SpaceX has long-term plan to catch Super Heavy booster in air with the help of launch tower catching arm. But in case SpaceX face problem with launch tower catching mechanism, then SpaceX needs to thinking about the another option to land Super Heavy booster successfully. SpaceX has hinted at an unexpected desire to develop marine recovery systems for the Starship program. Since SpaceX first began bending metal for its steel Starship development program in late 2018. CEO Elon Musk, executives, and the company itself have long maintained that both Super Heavy boosters and Starship upper stages would perform what are known as return-to-launch site landings. Since 2016, SpaceX has been making controlled landings of its Falcon 9 boosters to allow them to be reused for a number of years now. Such landings involve the rockets touching down, be it on a boat or a launch pad, using legs built into the rocket. But SpaceX CEO and founder Elon Musk has revealed different plans for the Falcon 9's bigger sibling, the Super Heavy, announcing the intention to have the launch tower arm catch the booster. Rocket retrieval and reusability has become an important focus not just for SpaceX but for other space companies, such as Rocket Lab, which, in addition to retrieving its Electron rocket after an ocean splashdown, has used a helicopter to catch a booster in midair. Their main reasons to catch Starship Super Heavy booster is, it has cost benefits. For reusing massively expensive rockets are obvious, and SpaceX's goal of catching its Super Heavy booster is also rooted in cost savings, as well as reducing the weight of the rocket. The announcement came, as they so often do, via tweet, with Musk saying the idea would be for the launch tower arm to catch the Super Heavy booster, with its grid fins taking the load. In a follow-up tweet, Musk revealed this approach would not only save money and mass by removing the need for the booster to have legs for landing, but would also allow it to be immediately repositioned onto the launch mount for reuse. Musk added that this would allow the booster to be ready to refly in under an hour, which sounds overly ambitious, but Musk and the SpaceX team can never be accused of aiming low. It's no longer clear if those long-stated plans are set in stone. Oddly, despite repeatedly revealing plans to develop marine recovery assets for Starship, SpaceX's recent marine engineer and naval architect job postings never specifically mentioned the company's well-established plans to convert retired oil rigs into vast floating Starship launch sites. Weighing several thousand tons, and absolutely dwarfing the football field-sized drone ships, SpaceX recovers Falcon boosters with. It goes without saying that towing an entire oil rig hundreds of miles to and from port is not an efficient or economical solution for rocket recovery. It would also make very little sense for SpaceX to hire a dedicated naval architect without once mentioning that they'd be working on something as all-encompassing as the world's largest floating launch pad. That leaves three obvious explanations for the mentions. First, it might be possible that SpaceX is merely preparing for the potential recovery of debris or intact floating ships or boosters after intentionally expending them on early orbital Starship test flights. Second, SpaceX might have plans to strip an oil rig or two, without fully converting them into launch pads, and then use those rigs as landing platforms designed to remain at sea indefinitely. Those platforms might then transfer landed ship, or boosters to smaller support ships, tasked with returning them to dry land. Third, and arguably most likely, SpaceX might be exploring the possible benefits of landing Super Heavy boosters at sea. Through its Falcon rockets, SpaceX has slowly but surely refined and perfected the recovery and reuse of orbital-class rocket boosters, 24 out of 103 of which occurred back on land. Rather than coasting 500 to 1,000 kilometers downrange, after stage separation and landing on a drone ship at sea. Those boosters flipped around, cancelled out their substantial velocities, and boosted themselves a few hundred kilometers back to the Florida or California coast, where they finally touched down on basic concrete pads. Unsurprisingly, cancelling out around 1.5 kilometers per second of downrange velocity, equivalent to Mach approximately 4.5, and fully reversing that velocity back towards the launch site is an expensive maneuver, costing quite a lot of propellant. For example, the nominal 25-second re-entry burn performed by almost all Falcon boosters likely costs about 20 tons of propellant. The average approximately 35-second single-engine landing burn used by all Falcon boosters likely costs about 10 tons of propellant. Normally, that's all that's needed for a drone ship booster landing. For return to launch site landings, Falcon boosters must also perform a large approximately 40-second boostback burn, with 3 Merlin 1D engines, likely costing an extra 25 to 35 tons of propellant. In other words, an RTLS landing generally ends up costing at least twice as much propellant as a drone ship landing. Using the general rocketry rule of thumb, that every 7 kilograms of booster mass reduces payload to orbit by 1 kilogram. And assuming that, each reusable Falcon booster requires about 3 tons of recovery-specific hardware. Mostly legs and grid fins, a drone ship landing might reduce Falcon 9's payload, to low Earth orbit by 5 tons, from 22 tons to 17 tons. The extra propellant needed for an RTLS landing might reduce it by another 4 to 5 tons to 13 tons. Likely less than coincidentally, a Falcon 9 with drone ship booster recovery has never launched more than approximately 16 tons to LEO. While SpaceX hasn't provided NASA's LPerf calculator, with data for orbits lower than 400 kilometers. It generally agrees, indicating that Falcon 9 is capable of launching about 12 tons with an RTLS landing, and 16 tons with a drone ship landing. This is all to say that landing reusable boosters at sea will likely always be substantially more efficient. The reason that SpaceX has always held that Starship's super heavy boosters will avoid marine time recovery is that landing and recovering giant rocket boosters at sea is inherently difficult, risky, time-consuming, and expensive. That makes rapid reuse, on the order of multiple times per day or week, almost impossible and inevitably adds the cost of recovery. Which could actually be quite significant for a rocket that SpaceX wants to eventually cost just a few $1 million per launch. However, so long as at sea recovery costs less than a few $1 million, there's always a chance that certain launch profiles could be drastically simplified, and end up cheaper, by the occasional at sea booster landing. If the alternative is a second dedicated launch to partially refuel one Starship, it's possible that a sea landing could give Starship the performance needed to accomplish the same mission in a single launch, lowering the total cost of launch services. If, like with Falcon 9, a sea landing could boost Starship's payload to LEO by a third or more. The regular sea recovery of super heavy boosters would also necessarily cut the number of launches SpaceX needs to fill up a Starship moon lander by a third. Given that SpaceX and NASA have been planning for Starship tanker launches to occur approximately 12 days apart, recovering boosters at sea becomes even more feasible. In theory, the Starship launch vehicle, CEO Elon Musk has recently described, could be capable of launching anywhere from 150 to 200 plus tons, to low Earth orbit, with full reuse and RTLS booster recovery. With so much performance available, it may matter less than it does with Falcon 9 and Falcon Heavy, if an RTLS booster landing cuts payload to orbit by a third, a half, or even more. Thanks for watching this video, and it's a super interesting topic. If you like this, to make sure you can subscribe. If you have any crazy idea what we should cover in next video, please comment it below, and we will see if we can get that. And thanks again for watching, and goodbye.